Now moving on to NMR, describe the NMR spectrum of the chloro compound. Presumably it means the proton, so we'll go ahead and do the proton, especially as was given in the answers. So here we are, we've got 3, 6, 9, 11 protons, but obviously this methyl, and this methyl are all the same. So those are going to be identical protons there, and then the 2 protons here, this CH2 will be same as each other, but different from these other 9 ones. So 2 types of hydrogens, so 2 peaks. Okay, now where would we expect them to be? Well, there's the methyl group, CH3, bonded to something else, so it's going to be at about 0.9, and then this one here will be a little bit further downfield because it's bonded to a C double bond O, and so it will be here between 2 and 3. Relative peak areas, that's easy, 9 to 2, you've got 9 of the red ones, 2 of the blue ones. And any splitting pattern, well, splitting pattern is due to hydrogens that are on the carbon are bonded to the carbon on which the hydrogens of interest reside. In other words, you're looking at hydrogens on adjacent carbons. Well, if we look at all the red ones here, their carbon's bonded to a carbon, has no protons on it, and the CH2 bonds to 2 carbons that have no protons on it, so therefore there will be no splitting pattern at all. Fungi, consumption, poisonous. Asian mushroom has a very toxic compound G. The peak areas in G are 1 to 1 to 2. It's got a carboxylic acid proton responsible for peak one of the ones. So what's suggested by the remaining peak areas 1 to 2? Well, that there's seen as how the carboxylic acid proton is 1. That means that this 1 must be another hydrogen and this 2 must be 2 other hydrogens. So it's only 3 other hydrogens in the molecule. 2 of them are equivalent and the other one is different. Now, the A-level answers indicates that you should be able to get a little bit more than that. Anything else is pure speculation given the information that we have here. One raw materials to make polyester P is methylbenzene, so that's the formula of methylbenzene. Methylbenzene can be converted to a mixture of dimethyl isomers and benzene. Gas chromatography can be used to separate dimethylbenzene isomers. One of the dimethylbenzene isomers has the C13 NMR below. How does this spectrum show that the isomer is 1,3-dimethylbenzene? Well, there are, of course, drawn kind of nastily, but just to emphasize some things, the 3 possible isomers, 1,2, 1,3, and 1,4, leaving out all the hydrogens because we only care about the carbons. Now, if we look at the 1,2, then you've got 3 aromatic peaks. You've got the 2 carbons are identical, they're bonded to methyl groups, then you've got the carbons that are bonded to those, and then the carbons that are bonded to those. So C1, C2, C3, C1, C2, C3, 3 aromatic peaks, and of course 1 methyl peak for the 2 identical methyl groups. Let's go to 1,3. Again, we've got the methyl groups, but now let's look at the carbons. You got C1, that's a carbon bonded to a methyl group. C2 is the carbon in between those 2. C3, going around the other direction, is the carbon bonded to the carbon with the methyl group, and then C4 is the one bonded to the 2 C3s. So in other words, in 1,3-dimethyl, there's 4 aromatic peaks expected, and of course 1 methyl peak. Then we get to the 1,4-dimethyl, very, very symmetric. There's only going to be 2 aromatic peaks. You've got one type of carbon that's bonded to the methyl, and then a type of carbon that's bonded to the methyl carbon and not to the methyl carbon. So only 2 aromatic peaks, 1 methyl peak. So we look at what we've got here. There's the aromatic area. There's the methyl area. Obviously, the methyl area is not going to help us at all, but the aromatic area very distinctly has 4 peaks, thus has to be the 1,3-dimethyl. Use the displayed formula of 1,4-diaminobenzene to help describe its high-resolution NMR spectrum. So there we go. Let's actually throw in some hydrogens into our pretty little picture. So each of those carbons there that's not bonded to an NH2 has a hydrogen on it. And then, of course, each nitrogen has 2 hydrogens on it. Now, looking at this, there is absolutely no doubt whatsoever that each of these 4 aromatic hydrogens is identical, and each of the hydrogens on the nitrogen is identical. So therefore we're only going to see two types of protons. The red aromatic ones will be here somewhere between 6.5 and 8. Now I've said it's a singlet. Why will it be a singlet? Well, because this carbon bonds to there, doesn't have a proton, bonds here, that's got the same type of proton on it, and this isn't going to split this isn't going to split that, so it'll be a nice singlet. The blue amine ones will also be a singlet because the nitrogen goes to a carbon that has no protons in it. But you'll see here nowhere in your beautiful little data sheet does it list NH, because NH are going to be very spread out all over the place depending upon the level of hydrogen bonding. So it's very hard to predict where these will shift to. Analysis of the compound shows C4H7Br. There's the high-res NMR spectrum. Student discussed it might be one of these following. Discuss the splitting pattern seen to decide whether the compound is N, L, M, or N. Give reasons. So let's look first of all here. This is a hydrogen that is next to a carbon that's got 3 hydrogens. So in other words, we've got to have a methyl group in there to give us this 1, 2, 3, 4 splitting pattern. This here is a singlet, and so it's hydrogens next to a carbon that have no hydrogens on them. And then this here is a doublet, which means these hydrogens come from a carbon that has 1 hydrogen on it. So we know for sure we got to have a carbon, got to have a methyl group next to a carbon that's got a hydrogen on it. We've got to have at least 1 carbon that has no hydrogens, and we've got to have a carbon that's got 1 hydrogen. Now let's look at the structures. First of all, L, because we don't have a methyl group. We don't have a carbon that has 3 hydrogens on it. M and M we do. There's the methyl group, and then there's 2 methyl groups here in N. Now let's look at M and see what we got. And we got a carbon with no hydrogens there, but we don't have a carbon with 1 hydrogen. We've got to have a carbon with 1 hydrogen to give us this doublet. So therefore M cannot be it. So now let's look at N, just to make sure, and I've color coded it here. So we want a methyl group that's next to a hydrogen so that that hydrogen can be split into 4. Well, that's that red hydrogen that bonds to a carbon that's got the 3 hydrogens on it, these 3 hydrogens splitting that one. Then we've got to have hydrogen, quite a few of them, with that nice singlet next to a carbon with no hydrogens. This methyl group here, those hydrogens are not going to be split at all because this carbon has no hydrogens on it. And finally, we've got to have green hydrogens, quite a few of them, because this is quite a nice high doublet there that's next to a carbon with 1 hydrogen. Well, there's those CH3s next to a carbon with 1 hydrogen. And there we are. I even tell you what they are. Now moving to carbon-13 for the same set of L, M, and N compounds. But how would carbon-13 distinguish these from bromocyclobutane, which is right there? Okay, well, let's just look at how many different types of carbon there. In compound L, you've got 1, 2, 3, 4 different types of compounds. Very distinctly different. Same thing for M. Here's the methyl group, there's the CH2, so those are different. Here's a carbon with a bromine, so that's different. And here's a carbon with a double bond, so that's different. So again, 4 types there. Compound N, we got a methyl, then a carbon and a double bond with a bromine, and methyl on the carbon and a double bond with a bromine. So again, 4 different types of carbon. And you can see here for the bromocyclobutane, as I've immediately drawn it, you've got the carbon bonds to the bromine, you've got the 2 carbons bonded to that carbon, which are identical to each other, and then you've got a 3rd type of carbon bonded to those 2. So first giveaway would be that the carbon-13 spectrum for these 3 would have 4 peaks, and for this one would just have 3 peaks. And of course the other one is relatively straightforward. You've got carbon-carbon double bonds, which occurs 90 to 150 in L, M, and N. You don't have one of those in the bromocyclobutane. Bromocyclobutane, you're going to have these 5 to 40, or R to bromine between 10 and 70. So either the number of peaks or the presence of this downfield double bond peaks.